All right, let's go ahead and get started for today. So today we're going to be covering kind of an introduction to steady state sinusoidal circuit analysis. So the first example I'd like to work, I believe, is fairly straightforward. So let's say that we have the following time domain circuit. Where this is a current source IS of t. And draw this a little bigger here. We have a 120 ohm resistor here, a 40 ohm resistor here, a 60 millihenry inductor, and a 12.5 microfarad capacitor. I'm going to draw that on the other side actually. And our ultimate goal is to find voltage drop over this inductor with respect to time, where we know that IS of t, our excitation function, is 500 cosine 2000 t plus 12 degrees milliamps. Now, hopefully, from watching the video and seeing me struggle through some of the math on last Friday, you guys have realized that approaching a circuit like this in the time domain is an absolutely terrible idea. So we are going to avoid that entirely by working in the frequency or phasor domain. So our first step is simply going to be to convert the circuit from the time domain into the frequency domain. So I'm going to redraw it. All of my components are going to stay the same, but their values are going to be significantly different. So the first thing that I'm going to do here is I'm going to convert my voltages and currents into their frequency domain representation. So if we have a time domain current of 500 cosine 2000 t plus 12 degrees milliamps, what is its frequency domain or phasor representation? So when we want a phasor, we literally keep track of two pieces of information, the magnitude and the phase angle. So my frequency domain current IS will be 500, because that's the magnitude we have here, with an angle of 12 degrees, because that's the phase angle we have, milliamps, all right? So our function was a cosine function. We didn't need to apply any trig identities or anything like that. Literally, we're taking the magnitude and the phase angle, and that's the only information we are carrying along into our frequency domain analysis. So we're going to have 500 angle 12 degrees milliamps goes here. For those of you that watched the video, hopefully hopefully most of you did. Sorry, we're also going to have some phasor voltage, which I'm just going to call VL with a bar over it to let us know that that's going to be a complex number. All right, so for those of you that watched the video, what is the impedance of my resistors going to do? Exactly right. So the impedance denoted by Z of a resistor is simply the resistor value itself. So our 120 ohm resistor remains a 120 ohm resistor, and our 40 ohm resistor continues to be a 40 ohm resistor. What is going to happen to our inductor? Well, the impedance of an inductor is J omega times L. So that's going to be J, what's omega? 2000, right? So omega is this bit right here, the guy that's multiplied by time inside of our trig function. So it's going to be 2000 radians per second. And then let's see, L is going to be 60 times 10 to the minus 3 henries, where a henry is a volt second per ampere. So we can see that we're going to have seconds multiplied by per seconds is going to give us units of volts per amps or ohms, which is good. So 2 times 10 to the positive 3 times 60 times 10 to the minus 3, I believe, is J 120 ohms. Lastly, we have to take into account the impedance of our capacitor, which is, can be expressed in one of two ways, either 1 divided by J omega C or negative J divided by omega C. Those represent the exact same thing because 1 over J is the exact same thing as negative J, when we talked about that in our complex number lecture. So we're going to have negative J divided by 2000 radians per second times our capacitor value, which was 12.5 times 10 to the minus 6 microfarads, where a farad is an amp second per volt. So again, we see that the seconds cancels the seconds here, so we're going to have 1 over amps per volt, which is the same as an ohm. And if we do the math here, I don't know that I can do this one in my head. So 1 over 2000 times 12.5 times 10 to the minus 6 minus J 40 ohms. We should see, and by should, I mean if we don't, we've made a terrible mistake. The impedance of an inductor is always going to be positive, and the impedance of a capacitor is always going to be negative. So now we have redrawn our circuit in the frequency domain. It's literally a two-step process. Convert all of our voltages and currents from the time domain to the frequency domain, meaning we represent them with phasors, and then convert all of our other circuit elements into their equivalent impedances. So we're now analyzing this circuit at exactly angular frequency of 2000 radians per second, which means that we can treat this guy like a DC circuit. We're just going to have complex number relationships to deal with. So we have all of the information that we need given. How do you guys feel that we should approach determining this voltage VL? Current division. Okay, so I believe the suggestion is we find the current flowing through this branch and the current flowing through this branch. Once we know this current, I'm going to call this guy over here phasor current IR for the right-hand branch. And once we know that current IR, we can simply multiply it by the impedance of the inductor to get the voltage drop over the inductor. We can treat all of these elements effectively as if they were resistors and just use DC circuit analysis techniques. Okay, so using current division, we would have our phasor current IR is going to be 500 angle 12 degrees milliamps multiplied by, let's see, 1 over 40 plus J 120 ohms. That's the total series resistance of the right-hand branch divided by 1 over 120 minus J 40 ohms, the total series resistance of our middle branch, 1 over 40 plus J 120 over here. So if you'll notice, I have left this expression as a mix of polar form complex numbers and rectangular form complex numbers because my calculator does not care, okay? So take a moment. I'll clear all this jibber jabber out of my calculator's memory. So take a moment and perform this calculation, okay? This is literally the level of complexity of calculations that you're going to be expected to do on an exam. All right, how many of you got one of the two answers that I have listed here? I see one person raising their hand. You may be the only person that actually typed stuff into their calculator in a timely fashion. We got a couple of more people raising their hands. All right, great. We're up to roughly half of the class, so that's good enough for me. All right. The reason why I put both answers out is because I don't have a personal preference as to which way that you particularly give me your answers. That being said, like whether you prefer polar form versus rectangular form means absolutely nothing to me. That being said, on the exams, because you're not going to be able to fill in a number, you're going to have to select a number. You need to be able to quickly go back and forth between these two different forms using your calculator, meaning that the answer for some problems may be expressed in rectangular form. And if you're comfortable getting everything in polar form, you need to know how to get to that and vice versa. So now that we have performed this calculation, how do we get that voltage VL again? So we know what that current IR is. How do we get VL? Right, multiply the current times the impedance. So we're treating all of these impedances as if they were a resistor. So it's just good old Ohm's law. This is the biggest fundamental hurdle that you guys have to get over with this new material, is that it's just the same as the DC circuit analysis. Everything that worked during our DC circuit analysis portion of the class will work here. So you shouldn't, if you have a current and you have an impedance, that's the same as having a current and a resistance, right? Getting the voltage shouldn't take you 15 to 20 seconds to figure out, gosh, what operation do I need to do? At this point, Ohm's law should be burned into your brain, okay? So using Ohm's law, VL is simply going to be the current flowing through the inductor multiplied by the impedance of the inductor, which I'm going to do this expressed in terms of the polar form, 353.553 angle negative 33 degrees milliamps multiplied by J 120 ohms. Gives me 42 point, go away, Dropbox window thingy. Or, sorry. 26, angle positive 57 degrees volts. Or for those of you that prefer rectangular, 23.107 plus J 35.582 volts. So my question to you guys is, was this the only way to work this problem? Good God, no, right? Hopefully that long video where I worked that one problem, I don't know, 6 or 7 different ways, illustrated that you can really get away with just using whatever you're comfortable with here. So another way that we could have approached this problem is recognized that this forms a practical current source. So we could do a source transformation and then voltage, which would put, we'd have a voltage source in series with 120 ohms, in series with minus J 40 ohms, in series with 40 ohms, in series with positive J 120 ohms, and then just done voltage division. We could have combined all 4 of these impedances together, multiply that by the current to get the total voltage drop between this point and this point in the circuit, and then used either voltage division or Ohm's law to figure out what that particular voltage is. There's always going to be lots and lots of different ways to approach these problems. So I just want to make you guys aware of that. Whatever you're comfortable with, chances are it's going to work. All right. Any questions on this guy before we move to something else? Hopefully this one was fairly straightforward. I'm just looking in an old textbook, finding things that are, yeah. All right, here's something. So this circuit is given to us in the frequency domain, so we don't need to do any conversion there. We have a current of 10 angle negative 45 degrees amperes. Minus plus 6 phasor current IX. This will be 2 ohms. This will be J1 ohm. Here's B. I want to find the Norton equivalent circuit of this network, where this is my phasor current IX, right? So to be clear, what I am attempting to do here is to convert the circuit on the left-hand side to this, where that box is just my generic circuit element representation of an impedance, because I have no idea if it's going to be purely resistive, which would be represented by a resistor, purely capacitive, which would be represented by a capacitor, purely inductive, which would be represented by an inductor, or some combination thereof. So that box just means a generic circuit element which has some impedance. So how am I going to approach this? So it depends on what I'm looking for. And let me be clear about that. If I were trying to find the Thevenin voltage, meaning that my terminals A and B were open circuited, I could apply current division and find IX. However, if I were trying to find I Norton, this set of terminals would be short circuited and I could no longer apply current division, because I can't say that none of the current is going to split off and flow through that dependent source. So that's why I'm hesitant to say yes or no. It really depends on what quantity that we're trying to find, which begs the question, which quantity do you guys want to find first? So our options are the Norton current, which we need because we're trying to find the Norton equivalent circuit. We could try to find the Thevenin impedance directly, or we could find the Thevenin voltage, which could be used to find the Thevenin impedance once we know the Norton current, or could be used to find the Norton current once we know the Thevenin impedance. We gotta determine at least 2 out of those 3 quantities. So somebody tell me something to do. The Norton current, is that what you said? All right. So our goal is to find the Norton current, and I'm going to assume that its direction is down. I am going to attempt to find the Norton current without, I was about to say without applying mesh analysis, but that might be difficult. I think it can be done though, so let's play around with a couple of things here. The reason why I'm trying to avoid using mesh analysis or nodal analysis, although nodal analysis may work here. The reason I'm saying nodal analysis may work is because if we grounded this guy, that would be our only unknown voltage, right? One equation, one unknown. Our calculators can do that all damn day, right? When we get to 2 equations, 2 unknowns, 3 equations, 3 unknowns, etc., the calculators that we allow for this class literally cannot do the system of equations because it involves complex numbers. So we're always going to be looking for ways to simplify things to not involve doing that. So my initial thought was actually going to be to transpose the 2 ohm resistor with the J1 ohm inductor and then do a source transformation on it to get this from a 3-loop circuit to a 2-loop circuit. But I think applying KCL at the top node is actually the quicker route to get the solution here. So effectively doing nodal analysis at the 1 node we don't know the voltage for, right? So if I do KCL at the top node, let's see what falls out of this thing, right? Where currents that are leaving will be positive, I'm going to have negative 10 angle negative 45 degrees amperes plus, now let me think about this real quick. So the reason why I'm hesitant even here is because I forgot something fundamental. We have a supernode in this case between node A and ground, which is at node B. So we know that VA is exactly equal to -6 IX. And we know that IX is VA over 2 ohms. Right? Anybody got any beef with what I've done thus far? So if we do substitution here, VA is equal to -6 times VA over 2 ohms, which tells me that, let's see, -6 over 2 is 3. 4 VA is equal to 0. Right? Anybody got any problem with my algebra here? Or anything that I've done to this point? Anybody see anything hinky looking? Everybody's groovy. All right. So from this, what must our nodal voltage VA be? 0 volts. All right. So here's the $1 million question then. What's I Norton? Incorrect. So if VA is 0 volts, then that means this current IX is 0 volts, right? So there's no current flowing this way, and there's no current flowing this way. So all of the 10 angle -45 degrees amps of current is going to flow here. None of it's going to split, flow here. None of it's going to split. I Norton must be, as Mr. Joe has pointed out, 10 angle -45 degrees amps. So this one's a little tricky.
Why does it not go down the paths? Why does it not split?
All right, so if we have 0 volts here and 0 volts here, what's the voltage drop over the 2 ohm resistor?
0.
Okay, So 0 volts divided by 2 ohms is what?
Still 0.
0 amps, right? So that means no current can flow down through the 2 ohm resistor. For the exact same reason, no current can flow down through the J1 ohm resistor or inductor. Ms. Robles asked me to highlight the supernode, so I'll do that real quick. So the supernode is wherever we have a voltage source, we're just including that. So that's this guy right here, where we could actually extend this whole thing to be the ground if we so included. And anytime our supernode contains ground, we don't have to have a Kirchhoff's current law equation, which was why I stopped writing one as soon as I noticed that our supernode contained our reference. All right. So are we all in, I don't want to say agreement, but acceptance that I Norton in this case is 10 angle negative 45 degrees? Can we think of any reason why it shouldn't be based on our circuit analysis? Let's start there. No. All right. So which of the other two quantities that we could find, V Thevenin or Z Thevenin, do you want to determine? The voltage. All right. So I'm going to redraw my circuit. Let's see. So we have 10 angle negative 45 degrees amps goes here. Here's terminal A, B, 2 ohms, J1 ohms. Here is where our current IX is defined. This is our quantity of interest, VTH. Now earlier, I believe Mr. Joes over there suggested that we could do current division with this circuit as it's drawn to find that current IX. And that is exactly how I'm going to approach this bit right here. What I'm doing might not seem super obvious at first, but it will actually get us our answer pretty dang quickly. All right. So if I apply current division, I can say that my phasor current IX is going to be that current 10 angle negative 45 degrees amps multiplied by 1 over 2 ohms divided by 1 over 2 ohms plus 1 over J1 ohms, right? I'm recognizing the fact that none of that current can split off and flow through the dependent source because it's connected to an open circuit, right? So the current flowing this way, by definition, must be 0. That's what's allowing me to do current division in this case. So if we do the math here, we're going to have 10 angle minus 45 degrees multiplied by 1/2 divided by 1/2 plus 1 over 1i is 4.472 with an angle of 18.435 degrees amps, or in rectangular form, 4.243 plus J 1.414 amperes. Bless you. All right, so does anybody have any questions, comments, concerns about how we have determined that phasor current IX? You're going to be doing an awful lot of current division and voltage division and things like that in these problems, just because that's usually one of the most effective routes. All right, now, how can we use this piece of information to determine Thevenin? Anybody got any ideas? Explain what you mean by that specifically. Right. So with the voltage drop over the 2 ohm resistor, you're saying we can find that. I concur, but let's look at this one step further. You're on the right path, Kendra, okay? So I'm gonna move this 2 ohms over here so we can see what's going on. I'm gonna call the voltage drop over the 2 ohm resistor a phasor voltage V2. And I'm going to write a Kirchhoff's voltage law equation around this loop. So using KVL, I would see negative phasor voltage V2 minus the voltage drop over our dependent source, which is 6Ix, plus VTH is equal to 0. Right? Anybody got any problem with that? So if I rearrange this guy, that gives me VTH is equal to V2 plus 6Ix, where V2 is twice Ix plus 6Ix simply gives me 8Ix. So that's what our Thevenin voltage is going to be, applying Kirchhoff's voltage law around that loop. Anybody have any problems with that? As long as I start at this node and end at this node, it doesn't matter what path I take, right? That's a great thing about KVL. So if I multiply my answer by 8, I simply get 35.777 angle 18.434, goodness, degrees volts, or 33.941 plus J 11.314 volts. So now that I have the Thevenin voltage and I have the Norton current, how would I find the Thevenin resistance, or Thevenin impedance in this case? Because that's what I'm actually looking for, right? We found I Norton up here, so we checked this guy off. Now we found V Thevenin, but we're looking for Z Thevenin. So how do I find that? Pardon? Ohm's law, exactly right. So Ohm's law tells us that Z Thevenin is simply our Thevenin voltage divided by our Norton current. So that is going to be 35.777 angle 18.434 degrees volts divided by 10 angle negative 45 degrees amps is going to be 3.577 angle, let's see, negative 63.566 degrees. Oh, so let me double check my math. I might not have done that right. 18.434 minus 45. Yep, got that wildly wrong. Negative 26.566 degrees. And if we wanted to, we could go through and verify that by turning off our current source and applying a test voltage to our network, to the open terminals of our network, and measuring the Thevenin resistance directly. But we got 10 minutes left and I don't want to do that. So we have enough time to do, but before I move along here, does anybody have any questions about any of the circuit analysis we did on this guy, right? Sure. Am I good to go? All right. So let's look at one last problem here. Um, bu- bu- bu. Plus, and let's say that Vs of t is 5. Let me see something here, just so I make these values 1 divided by. Okay. Cosine 2 pi times 100t plus. No phase angle. We got an op-amp circuit. we can still do our simple DC style circuit analysis on this circuit as long as we work it in the frequency domain. So how are we going to get this guy in the frequency domain? Let's do exactly what we did on the previous problem. We're going to convert our time domain voltage into a frequency domain or phasor voltage. All of our resistors, if you'll recall, are going to, nothing changes with regards to their impedance. This guy over here is going to be 5 angle 0 degrees volts. The impedance of our capacitor is going to be negative J divided by omega C, where omega is 2 pi times 100. And so I get negative J 6.366 ohms. So how would we go about analyzing this circuit? Right now, it looks a little ugly, right? So our basic steps for solving an op-amp circuit, if you recall from a couple of weeks ago whenever we did it, where we applied our ideal op-amp rules, number 1 and number 2, which means that we have this current is equal to 0 and this current is equal to 0. That's ideal op-amp rule number 1. Ideal op-amp rule number 2 tells us that whatever voltage we have here at the non-inverting terminal, the exact same voltage occurs here. Then we would determine what our voltage at our non-inverting terminal is, which in this case is just 0. We can see that the non-inverting terminal is connected directly to ground. And then our next step was to perform Kirchhoff's current law at our inverting input node. So we would say this current plus this current is equal to 0, and that would allow us to solve for V out. The problem that we're going to have here is that we're going to have 0 volts minus some unknown voltage divided by 20 kilo ohms, right? So we're going to run into some problems here because we don't know the voltage at this node. So what could we do to simplify this circuit to be able to apply our basic formula or algorithm for solving ideal op-amp circuits? So let me draw what I would argue would be an ideal case would be. So if we had an op-amp circuit like this, we can analyze it all day long. We've done this multiple different ways. In fact, we could just recognize that this is an inverting amplifier, and we would know that our output voltage is just going to be simply negative Vn times ZF over Z1 based on the lab that we did. So my question to you guys, and we're running out of time here, is how do we get from this circuit in the middle to this circuit on the bottom? The circuit in the middle, arguably difficult to analyze. The circuit on bottom, fairly trivial. So you're asking if the capacitor and the resistor are in parallel. So I was about to ask which resistor you're talking about, but none of them are in parallel. Now we do have a virtual ground here, so I could see your argument that maybe this guy could be treated as in parallel there, but that's not really what I'm going for, because while this has a potential of 0 volts, that makes me nervous. Let's just put it that way. Saying that these two are in parallel makes me nervous. Nodal analysis could definitely work. So we could just call this guy some voltage VA and then go on from there. So we'd have to apply 2 separate iterations of Kirchhoff's current law, one at node A and the other at the inverting input terminal, where we're going to have 2 equations and 2 unknowns, which our calculators cannot take care of. So if this were a homework problem and we wanted to get our computer out and use MathCAD, but let's say this were a test problem, right? How can I do this while avoiding setting up a system of equations? Do any of you guys remember source transformation? Right? So what I have here is a practical voltage source. Everybody okay with that? So I could convert it into a current source, right? 5 divided by 20 kilo ohms is going to give me what? 5 over 20 is 1/4. So I'm going to have 1/4 angle 0 degrees milliamps. Now I have 20 kilo ohms, and this 20K is for sure in parallel with that capacitance, right? So I would have 20K in parallel with negative 6.366 J. So with these guys in parallel, I could replace them with a single generic impedance, and I'm going to call this ZEQ1, where ZEQ1 would be 6,000, so 6.066 angle negative 72.343 degrees ohms. So I've made it slightly less complex. What could I do now? Go back to a voltage source representation, right? So if I multiply that guy by that 0.25 milliamps. I get 1.517 angle negative 72.343. My ZEQ 1 comes up here. And now I could add to my ZEQ1 this other 20 kilo ohm resistor that's been placed in series. And then I have the bottom circuit, which is very easy to analyze. So don't forget to think about things like that, means by which to, simplify the circuit. And we're out of time with regards to actually analyzing and all that kind of stuff, but it's trivial at this point. But don't forget to think about things like that, where you can do source transformations and stuff like that to make your circuit more easy to analyze, right? If you see something that looks funny to you, chances are you may need to do a little bit of shifting, right? Source transformations, things of that nature. You can combine impedances regardless. You know, now you have a means by which to add resistors and capacitors in series and all that kind of good stuff. So be thinking about that kind of thing when you approach these problems. All right, so I will see you guys on Wednesday for more practice with these and a lab. I'm actually going to send out a poll because I think with as many people that have dropped this class, we might actually be at a safe level to have everybody meet at the same time. So would anybody, just a very informal, would anybody be opposed to getting the full hour and 50 minutes instead of just 50 minutes? Okay, well, I'll put something up on Moodle, and if anybody doesn't like it, we'll keep the arrangement that we have, but we might move from there. All right. So something that I mentioned at the end of the last section, I'll mention to you guys here at the beginning. So if you will notice, the room has significantly thinned out since the beginning of the quarter. I believe at my last count, which was before class on Friday, and I think people have dropped since then, that we are under the threshold for how many people can be in this room simultaneously, which means we could merge the early section and the later section into one thing, and then we could work on stuff for an hour and 50 minutes as opposed to 50 minutes at a go. So would anybody be opposed to doing that? Yeah. I mean, if it doesn't work with your schedule, I understand that, because we've been doing it one way for the entirety of the quarter, and now that we're in the last 3 weeks, I'm asking for a change. So if it doesn't work, I understand that. But if anybody isn't opposed to it, then I think it would probably better serve you guys getting a little bit more time with me to work on some stuffs. Now, I'm not saying, oh, you don't have to watch the videos and all that kind of crap anymore. It's not remotely what I'm saying. I'm saying do that, and then we'll also work on stuff for effectively 2 hours instead of just 1, so that we can work more examples and spend more time answering questions, et cetera, et cetera. Does that seem reasonable? Okay, I will put a thing up on Moodle doing an official query or poll to make sure everybody's okay with it. But that's what I would like to do moving forward, because I think it would be of the most benefit to you all. All right, so I'm trying to decide if I want to work the same problems that I worked earlier or new problems, and I'm kind of leaning towards new problems. I may only get to work 2 instead of 3, but let's go for it. All right. So there's our first problem. a 1 microfarad capacitor, 30 ohm resistor, a 1.2 millihenry inductor, and our goal is to find the voltage drop over our inductor, VL of t, and our source is supplying us 40 cosine 5 times 10 to the 4 t plus 22 degrees volts. So before we begin here, hopefully the amount of terrifying trig and calculus and all that jazz that was done on Wednesday, or not Wednesday, last Friday, was enough to convince you that working these type of problems in the time domain is a absolutely terrible idea. So instead, we are going to focus all of our circuit analysis from here on out to be in the frequency domain, okay? So in the frequency domain, all we're going to do is convert all of our voltages and currents into phasors, and then convert all of our resistances, capacitances, and inductances into impedances, okay? So I'm going to redraw our circuit. Yes. So, first question for you guys. How do we convert our time domain source voltage into a frequency domain source voltage? Or a phasor? Anybody remember anything from the videos regarding phasors? All right, I don't have time for that. There's two pieces of information that you need to carry, all right? The magnitude and the phase angle. That's it, okay? As long as your voltage signal is a cosine function, that's all you need, okay? So in the frequency domain, we would represent 40 cosine 50,000 t plus 22 degrees as literally just 40 angle 22. We throw away the frequency information, we keep only the magnitude and the phase angle. So we have 40 angle 22 degrees volts right here. Does anybody remember anything about the impedance of a resistor? The impedance of the resistor is the same as a resistor value. So that means our 30 ohm resistor continues to be a 30 ohm resistor. What about the impedance of an inductor? So the 1 over j omega bit, that's the capacitors. For inductors, it's j omega L. So that would be j times 5 times 10 to the 4 units of per second multiplied by 1.2 times 10 to the minus 3 Henry, where a Henry is a volt second per amp. So the seconds and the per seconds cancel each other out. So we have units of volts per amp or ohms. And so that is, let's see, 1.2 times 1.2 times 10 to the minus 3 times 5 times 10 to the positive 4 gives me J60 ohms. So this is going to be J60. Here's my phasor voltage over my inductor. And then ZC is 1 over j omega c, as Ms. Dugas suggested. Or we can write this as negative j divided by omega c, because 1 over j is the exact same thing as negative j, which we proved in the complex number lecture thing. So that would be negative j divided by 5 times 10 to the 4 per second multiplied by our capacitor, which is 1 times 10 to the minus 6 amp seconds per volts. The seconds and per seconds cancel out, so we have 1 over amps per volts, which is the same as a volt per amp, which is an ohm. And from this we get, let's see, 5 times 10 to the 4 times 1 times 10 to the minus 6 minus J 20 ohms. So we have converted from the time domain to the frequency domain. So now we are at a point where, other than these pesky complex numbers, our circuit looks exactly the same as a DC circuit. So using simple DC circuit analysis techniques, how could I determine that voltage VL? I'm not using calculus-based relationships at all anymore. This is simple DC circuit analysis. If I had a 20 ohm resistor here and a 60 ohm resistor here, how would I find that voltage over the 60 ohm resistor? So the J60 ohm resistor, which is the inductor, is in parallel with a 30 ohm. So I'm going to take what you suggested by observing that they are in parallel one step further, and I'm going to solve for that voltage VL directly using voltage division, right? Where I'm going to say that in series with this minus J20 ohm resistor, I have some equivalent impedance from that resistor and inductor that are in parallel, okay? So from that, VL is going to be my source voltage, 40 angle 22 degrees volts, multiplied by, so now I'm looking for the voltage drop over those two elements that are in parallel. So that's going to be 30 times J60 over 30 plus J60. And then I look for the total series impedance seen by my source, which is negative J20 plus those two guys in parallel, 30 times J60 over 30 plus J60. And there we have it. So take a moment or two and calculate this. Now notice real quick here, before you get to typing stuff into your calculator. Oh goodness, that is not what I needed. I have a polar form complex number being multiplied by some combination of rectangular form complex numbers. Your calculator does not care, okay? It can do this operation. You don't need to convert back and forth and this, that, and the other. Literally type it in like this, and your calculator should be good to go. Put the I on the other side of 60.
Oh, yeah.
Yep. Has anybody gotten an answer? All right, so I provided the answer in both polar and rectangular form because I don't particularly care which way you guys do it. Like your preference could be polar, or it could be rectangular, or it could be whatever your calculator happens to be set to that you don't know how to change. Any of those are okay. I will say on the exam and stuff like that, because you don't get to like write in a number or anything like that, you do need to be familiar with how to quickly convert from polar form to rectangular form using a calculator, which again should be fairly straightforward for everybody with a TI. It's just going into the complex menu. Option 4 converts to polar form. Option 5 converts to rectangular form. If you have the Casio 115s, you hit second 2 to go into your complex menu, and then it should be options 1 and 2 there. And for those of you with the 991, you hit the option button down, and then it lets you convert from polar to rectangular and vice versa. All right, so we found this voltage VL. We want the time domain voltage VL of t. How do you think we get back? So we were working in the frequency domain. Now we want our time domain voltage. So what do we do? Exactly right. So the polar form of the answer has a magnitude and a phase angle, and we know that the excitation frequency is the frequency at which everything in this circuit is going to oscillate. That's what allows us to do this frequency domain circuit analysis. So we would simply have 42.426 cosine omega t, where omega is 5 times 10 to the 4t, plus 67 degrees volts. Now, some of you may be thinking to yourself, well, gosh, how in the heck did I get a larger voltage, right? We did voltage division, and this number is larger than our source voltage. We have to realize that these two voltages are considerably out of phase. One has a phase angle of 22 degrees. The other one has a phase angle of 67 degrees. That's where that discrepancy is going to come from, okay? So even though it may seem like it's larger, and it does have a larger amplitude, that literally has no bearing on anything. Effectively, this circuit is a simple passive amplifier, is one way to think about it. If we look at what's going on right here, this negative J20 ohms in the numerator is making the in the denominator of our voltage division equation is making that denominator smaller than the numerator, which makes sense then that we should be making our signal bigger. So, all right. Any questions on this particular problem? Any of this circuit analysis, what limited circuit analysis we did, not make sense? All right. Was this the only way to work this problem? Let's start there. Not by any stretch. If you watched my silly 50-minute long video where I worked the same problem 7 damn different ways or whatever, you know that we can throw the kitchen sink at pretty much any one of these and we'll come up with the right answer eventually, okay? So whatever you're most comfortable with is where you should be approaching this. It's so simple to make bookkeeping errors with all of these complex numbers and stuff like that, that you really want to get comfortable with the basic circuit analysis techniques, because doing anything too particularly fancy will kind of bite you in the butt. All right, let's look at, that one looks like a pain in the butt. Yeah, we'll do this one. I did this one with the earlier group, but I thought it was a good problem. So this circuit is entirely worked in the frequency domain. Angle negative 45 degrees. All right, our goal with this problem is to get the Norton equivalent circuit, which, as a reminder, would be some phasor current I Norton in parallel with, instead of a resistance, we're going to have now a Thevenin impedance. And I'm drawing that impedance as a box because it is a generic impedance. I do not know whether it will be resistive, capacitive, inductive, or some combination thereof. So I'm just using a generic circuit element to stand in for my impedance. So my question to you fine folks is, how are we going to find these two pieces of information, the Norton current and the Thevenin impedance of this circuit? Or I guess a better question would be, which of the Thevenin voltage, Thevenin impedance, and Norton current do you wish to solve for first? Because we are going to need two of those three quantities, guaranteed. Thevenin voltage, all righty. So the Thevenin voltage is, by definition, the open circuit voltage seen between terminals A and B. I'm arbitrarily choosing the positive polarity terminal on top. So yeah, all right. So how might we go about analyzing this circuit to determine VTH? So I'm going to try to, mesh analysis would absolutely work. Let me start there. But the calculators that we're allowed to use in this class cannot solve a system of equations that has complex numbers in it. So we need to get in the habit of finding ways to avoid using nodal and mesh, if at all possible, because that requires literally the use of a computer. Or you could do it by hand using Kramer's rule if you want to get really, really tedious about matrix manipulation by hand with complex numbers, which I would be willing to bet most of you don't want to do. We can do it all day. It will take all day, but let's try to avoid that. So there are two ways that I'm thinking about right now. They're both effectively amount to the same thing, but they're in slightly different approaches. And so let me explain myself here. So I literally just said that I would like to avoid using nodal and mesh analysis, but if I call this guy down here ground, this top node VA, well, let's not do VA because there's already a node A and that might be confusing. So let's call this guy V1. I know that this guy right here, V2, is just 6Ix, whatever that happens to be, above V1. And I could perform KCL. So I know that current in this current and this current, because I know that this other current is 0 amps. No current's going to flow through the dependent source because it's an open circuit, right? Or it's connected to an open circuit. So I could get away with doing nodal analysis here effectively because I really only have one unknown voltage. Because once I know what V1 is, I know what Ix is, which means I know what V2 is. Another way that we could approach this without bothering to do nodal analysis at all is, again, recognizing that the current flowing through that dependent source is 0 amps. We can do current division to find out what that current Ix is. And then we can write a simple Kirchhoff's voltage law loop to figure out what VTH is. So instead of doing nodal analysis and a bunch of stuff, we can really get this just using very, very basic circuit analysis techniques. So using current division, I can say that Ix phasor is 10 angle minus 45 degrees amps multiplied by 1 over 2 ohms divided by 1 over 2 ohms plus 1 over J1 ohms. Right? That's going to tell me the current flowing down through that 2 ohm resistor. So let's take a moment to do that. What I get, oh, sorry, this is current division, so those should be amps, not volts. That's what I get for my current. Does anybody else get that? I see Shahara nodding her head yes. Anybody else? All right, so now you may be asking yourself, well, that's great that he figured out what the heck Ix is, but how does that help me? What I'm going to do, I'm going to move this 2 ohms label over here, and I'm going to call this voltage V2. Would you all agree that we have enough information to solve for that voltage V2 now that we know what Ix is? Just using good old Ohm's law, right? Well, if I start from this node and do Kirchhoff's voltage law around this path, I have negative V2 minus 6Ix plus VTH is equal to 0, which means VTH is simply V2 plus 6Ix, where V2 is just 2Ix. And so I can see that VTH is just 8Ix. So if I multiply my prior answer times 8, I get 35.777 angle 18.435 degrees. Volts, or in rectangular form, 33.941 plus J 11.314 volts. So I figured out what Thevenin is. Does anybody have any questions, comments, or concerns about the circuit analysis that I've done? Around that green loop, yes, sir. Just adding up voltages. Well, it's because you're multiplying by 8 angle 0. So when you multiply two complex numbers and one of them has an angle of 0, it means the angle of the other one does not change. Or you multiply a complex number by a real number, doesn't change the angle. All right. So we're all in agreement with regard to the Thevenin voltage. So which of the other two quantities do you want to solve for now? Norton current or Thevenin impedance? Current, all right. So I'm going to redraw my circuit. So my Norton current means that I short circuit my terminals A and B, and I'm going to look for the current down flowing through that short circuit. Where this guy here is still my current IX. I can't determine what IX is now by using current division, because since I've closed this path, I can't definitively say whether current is going to split off from that 10 angle negative 45 degree source and flow through the dependent source, right? There is a path for it to flow through, so I have to assume at a minimum that it's possible. So I can't use current division to figure out what IX is in this case. So with that in mind, if I did nodal analysis with the bottom node as my ground, literally my only unknown voltage is this guy V1, right? So I have a supernode. Between node 1 and ground, right? If I have a voltage source and I'm doing nodal analysis, I have a supernode. What does it mean, or specifically, what do I not do when my supernode contains the reference voltage? Anybody remember? So whenever my supernode contains the reference voltage, I don't need to write a KCL equation. Okay, that's one of the fundamental rules of simply have a voltage relationship. So my voltage relationship is going to be V1 is equal to negative 6 Ix, right? The voltage at the positive polarity terminal of my dependent source is 0. The voltage at the, so I'm going to have 0 minus V1 is equal to 6 Ix, or V1 is equal to negative 6 Ix. Everybody okay with my relationship there? All right. My other equation that I'm going to need, obviously I've introduced a new variable, Ix. So I need to express Ix in terms of my nodal voltage. How am I going to do that? Okay. So you're saying current is equal to voltage. There we go. And I'm going to substitute this relationship into here. So I get negative 6 times V1 over 2 ohms. 6 over 2 is 3. So I can see that V1 is equal to negative 3 V1, or 4 V1 is equal to 0. My algebra is correct here, which it is. What does that tell me about V1? V1 is equal to 0. Does that help me solve for I Norton? Immensely, okay? If V1 is 0, how much current flows through the 2 ohm resistor? 0 amps. How much current is flowing through the J1 ohm inductor? Pardon? Also 0, right? Because the voltage drop on this side is 0 minus the voltage drop on the other side is 0, so 0 divided by J1 is 0. So if no current can branch off and flow down through the 2 ohm resistor and no current can branch off and flow down through the J1 ohm inductor, what is I Norton? 10 angle negative 45 degrees amps. Absolutely right. So we've determined our Thevenin voltage. We have determined our Norton current. What's left? Right, we're trying to find, we got this guy, and we have enough information to solve for this guy. We just need to actually do it. So how do we get our Thevenin voltage? Or excuse me, Thevenin impedance. Yep, just good old Ohm's law, right? V Thevenin divided by I Norton. So that is 35.777 angle 18.435 degrees divided by 10 angle minus 45 degrees is going to be 3.578 with an angle 18 minus 45. 45. I'll do it with my calculator. 18.435 minus 45, negative 26.565 degrees. There we go. Any questions on this guy? Yes. So if no current can branch off, right? So we know that we have 10 angle negative 45 degrees amps flowing into this node. No current can branch off because if there's no voltage drop over the 2 ohm resistor, no current can flow through the 2 ohm resistor. So that same current flows into this node. Again, no current can branch off and flow down through the inductor because if there's no voltage drop over the inductor, there's no current flowing through the inductor. So all of that current must flow through the short circuit. All right. So we're not going to actually work this problem, but I want to talk about it because it's something something neat I could do on your test. We're not going to work it simply because we're going to run out of time. Sorry. Yep. Right there, where that little cloud is with the red dot, that says it's being recorded. So we have this op-amp circuit, all right? Now, how we have approached every op-amp circuit in the past is we apply op-amp rule number 1, which says that no current can flow into or out of the input terminals. And then we apply op-amp rule number 2, which says that whatever voltage we have at our non-inverting input terminal, which we can obviously figure out here, is going to be 0, is equal to the voltage present at the inverting input terminal. Our next step is to determine what V plus is, which in this case is 0. And then finally, we would apply Kirchhoff's current law at our inverting input terminal. So we'd find the current flowing through here and the current flowing through here and use those relationships to find V out. The problem that we would see here is that while this voltage is known, this voltage is unknown, right? So for instance, if I called this guy VA, I would have an equation that looks like, let's see, negative VA divided by 10 kiloohms minus V out over 20 kiloohms is equal to 0. I've got one equation and two unknowns, okay? So I would have to come up with some other equation. Now, let me draw something slightly different. circuit, which we've analyzed several like this circuit, except not with impedances, is a simple inverting amplifier circuit. And you may or may not remember, it's okay if you don't, we could do the analysis and figure out that in this case, V out would simply be our feedback impedance ZF divided by our input impedance Z1 multiplied by our voltage VF. That is the input-output relationship for an inverting amplifier circuit. So my question to you guys is, how would we convert the circuit on top to give us the circuit on bottom? What could we do? We don't need to actually do the math here. Let's just talk our way through it. Does anybody have any ideas? We have a circuit that would be difficult to analyze, and we want to convert it to a circuit that would be trivial to analyze. Sure. So if we did a source transformation, what would happen? You don't have to get into the specifics here, just describe what would be going on. All right, so this voltage source would become a current source parallel with a resistor. So this would be a 10 kilo ohm resistance. This would be a current source, direction up, and 5 over 10 kilo ohms. This would be, if I wanted to do the math here, half with an angle of 0. So let me. All right, what does that help? So there are multiple 10 kilo ohm resistors. So you are suggesting that we could use current division to find out how much current is flowing through this 20 kilo ohm resistor? I understand your logic, but I disagree. And the reason that I disagree is because we don't know how much current is coming out of the output terminal of the op amp. And unfortunately, there isn't a way for us to know how much current is coming out of the input terminal of the op amp without knowing the output voltage. So yes and no. Let me explain why I say yes and no. So we can combine this 10 kilo ohm resistor and this minus J5 kilo ohm capacitor because they're in parallel. We can do that all day. The reason why we can't combine it with this 10 kilo ohm resistor up here is because that guy isn't in parallel, right? So we could combine these two into a single equivalent impedance. So just for the sake of argument, that was what, 10K times 5, excuse me, minus 5 kilo ohms J divided by 10 minus 5I. ZEQ1, I'm going to call it, is 4.472 with an angle of minus 63.435 degrees kilo ohms. Exactly right. So now we would have ZEQ1 up here. If we multiply that by half of a milliamp, we get 2.236 angle negative 63.435 degrees volts. What can we do now? So we could, but it's unnecessary, right? Our goal is to get some impedance in the feedback, which we already have. We started with that, and a single impedance between the inverting input terminal and our voltage source. So that was 10K in parallel with minus J5K. So if we can combine impedances in parallel, why can't we combine them in series, right? So we would simply combine these two into a single equivalent impedance, and then we exactly have this bottom circuit, which is trivial to analyze. I'm just trying to get you guys to think about how we can make ugly looking things look like simple circuits that we know how to analyze. That's it. That's all I wanted to do with this little exercise here. Okay, so to be clear, on your exam, there will be steady state sinusoidal circuits that you need to analyze. They will never, ever, ever require the use of nodal or mesh analysis. Okay, you will be able to use techniques like source transformation and voltage division and current division and superposition and things like that in order to analyze every single one of them without ever setting up a system of equations. Okay, so get nodal and mesh effectively out of your head for the next 2 weeks. It's not gonna, I know this is the problem with you guys relying on it as a crutch to be able to do everything previously. Here's the time we can't do it because we don't have the benefit of having a computer with us when we take our exams and to be able to use MathCAD and things like that. So this is where all of those topics where I kept trying to tell you guys, hey, we're going to use this a lot. This is where it's going to come bite you in the butt if you didn't understand it, okay? So if I need to refresh your minds on current division, voltage division, source transformation, source combination, all that kind of jazz, let me know and we can do it. I can generate some problems and we can work through stuff like that. All right, I'm out of time for today. Yes, ma'am. Yes, it makes a big difference. So let's figure out why you got the angle as positive. So you treated the capacitor as minus J 5,000 ohms. All right. So I could have made a mistake here. I feel like I didn't, but let's see. All right. So we have 10,000 times minus 5,000 I over 10,000 minus 5,000 I. I still get a negative angle. So trying to think of how to describe this. All right. we're done, so I'm really just explaining this to Shahara, but if you guys want to listen, you're welcome to do it. So if we look on the complex plane here, where these are positive real numbers out this way, and these are imaginary numbers out this way, we had a resistance come out to roughly this way, and we had a capacitance, let's just say, come out to here. If they were in series, they would add together, and this would be Z. I'm going to call this RC, and we can notice that our angle theta, by definition, is less than 0 degrees, so it's negative. When you're getting a capacitor and a resistor in parallel, it's still going to come out with a negative angle, always, like by definition, because it is a capacitive load. Whenever you have an inductor and a resistor combined, it's always going to have a positive phase angle. The impedance will always have a positive phase angle associated with it. It's a little bit harder to see when they're in parallel. So for instance, so we have R multiplied by 1 over j omega c times R, actually let me write this slightly different, multiplied by negative j over omega c minus j over omega c, right? That's resistor in parallel with an inductor or capacitor. If I multiply this guy by its complex conjugate of the denominator, R plus j over omega c, R plus j over omega c, what I'm going to have is R squared minus j, hold on. All right, j times, so negative j times j is positive, so 1 over omega c times R divided by and I can write this as R over omega c divided by R squared plus 1 over omega c squared minus j R squared over omega c, R squared plus 1 over omega c quantity squared. So it's, even when they're in parallel, it's still got a negative imaginary component, which means the phase angle is going to be negative. So, complex math, yay. So much fun. I legitimately enjoy it, but you guys, I'm sure, hate it. Alrighty, see you guys on Wednesday. I'll send out a Moodle poll thing or whatever, and I would anticipate that, you know, we'll pretty much all agree to meet for the full 2 hours and work more examples and all that.